Very good day to everyone. Today I will be presenting my assignment for BSC121 Calculus 1A. So the content that I'll be covering today is applications of derivatives to economics, the washer method, as well as moment and center of mass. So let us start off with the applications of derivatives to economics. So a few functions that are used in economics are the cost function, average cost function, revenue function, average revenue function, profit function, and average profit function. So cost function is the total cost of producing Q units of goods, and the derivative of the cost function is the marginal cost, which is the additional cost of producing one more unit. And this derivative of the cost function helps identify the production level where costs are minimized. Then we have the average cost function, which is denoted by AC of Q, and the mathematical formula for average cost is the cost function divided by Q, which is the quantity of goods. So the derivative of the average cost function is the rate of change in average cost as output changes, and this determines the output level where average cost is minimized. Next, we have the revenue function, and the mathematical formula for the revenue function is P times Q, where P is the price per unit and Q is the quantity sold. Then the derivative of revenue function is the marginal revenue, which is the additional revenue from selling one more unit. And this helps businesses determine the revenue maximizing output level. And then we have the average revenue function, and the formula is the revenue function divided by the Q, which is the quantity of goods. And the derivative of the average revenue is the rate of change in average revenue as output changes. This identifies the relationship between total revenue and price elasticity. Next, we have the profit function, and the formula for the profit function is the total profit is equal to the total revenue minus the total cost. And then the derivative of the profit function is the marginal profit, which is the additional profit from selling one more unit. And this helps determine the profit maximizing output level. Last but not least, we have the average profit function, which is denoted by AP of Q, and it is equal to the profit function divided by the quantity of goods. And the derivative of the average profit function is the rate of change in average profit as output changes. This helps businesses identify optimal pricing and production strategies. So here's an example. Say a company produces a product, and the cost, revenue, and profit functions are defined as follows. So the cost function is 50 plus 5q plus 0.2 q squared. The revenue function is 20q minus 0.1 q squared, and the profit function is the revenue function minus the cost function, which totals to negative 0.3 q squared plus 15q minus 50. And keep in mind that Q is the number of units produced and sold. So if the company produces 50 units of goods, using the formula that was given, we can say that the total cost of producing these 50 units is $800. Then if the company sells 50 units of goods, the revenue from selling those units are $750. From there, we can see that the cost is greater than the revenue that the company has gained. So this means that the company faces a loss of $50. We can also calculate this using the profit function that was given earlier. Now we can also apply the derivatives of these functions mentioned earlier into the business. So the marginal cost is basically the derivative of the cost function. It is equal to 5 plus 0.4q. Using the formula, we can know that the cost of producing the 51st unit will be $25 when we substitute 50 into the q. This goes to the same with marginal revenue, which is the derivative of the revenue function, and we have found that it is 20 minus 0.2 q, and when we replace q as 50, we know that selling the 51st unit will increase revenue by $10. Lastly, we have the marginal profit, which is the derivative of the profit function, and it is equal to negative 0.6q plus 15. Now we set the derivative of the profit function to 0 to find the production level that maximizes profit. So using the formula, we can find that negative 0.6q plus 15 equals 0, and q will ultimately equal to 25. This means that at q equals 25, the company maximizes profit. Now, why is the profit maximization level at the derivative of the profit function equals to 0? So the derivative of the profit function is essentially a tangent line, and when it is set to 0, it means that the tangent line is a horizontal line. So from the graph, you can see that when the tangent line is horizontal, it reaches a critical point. So the profit function reaches a critical point where the rate of change stops. This indicates that the profit is either at a maximum, minimum, or inflection point. We can also use the second derivative test to confirm whether the critical point is a maximum or minimum. So the second derivative of the profit function, if it is less than 0, it is a maximum point as it is concave downward. And if it is more than 0, it is a minimum point as it is concave upward. So the profit maximization occurs when the firm produces at the level where marginal revenue equals the marginal cost. This implies that at profit maximizing level, the revenue gained from selling one more unit equals the cost of producing that unit, and producing beyond this point will reduce profit. Now let us move on to the washer method. So the washer method is essentially a technique used to calculate the volume of a solid of revolution when the solid has a hollow region in the center, resembling a washer-like shape. This method subtracts the volume of the hollow part, which is the inner radius, from the volume of the entire solid, which is the outer radius. There are a few steps to the washer method. Firstly, we sketch the region that will be revolved. Then we identify the axis of rotation, whether that is about the x-axis, y-axis, or other vertical or horizontal lines. Then we find the inner and outer radii of the washer. The inner radius, which is denoted by the small r, is the distance from the axis of rotation to the nearest boundary of the region. The outer radius, which is denoted by the big R, is the distance from the axis of rotation to the farthest boundary of the region. Next, we can find the limits of the integration by identifying the interval over which the region exists, either in terms of x or y. Then we can finally set up the volume integral using the formula v equals to pi times the integration of big R squared minus small r squared from a to b. And finally, we can evaluate the integral. Now here's an example of finding a volume of a solid with a hollow inside using the washer method. So a solid is generated from revolving the region bounded by the curve y equals square root x, the line y equals 1 over 2x, and x equals 4 about the x-axis. So the graph on the left shows the area of the region in a 2D plane. And when it is revolved around the x-axis, we get the graph on the right. So from the graph, we can see that the outer radius is the curve y equals square root x, while the inner radius is the line y equals 1 over 2x. We can also see that it is bounded by the intervals 0 to 4. So from those information, we can put it into the formula and find the volume. So we can finally solve the volume of the solid through the steps on the right, and in the end we get the volume as a pi over 3. Lastly, let us talk about moment and center of mass. So the moment of a particle with respect to a point is the product of the particle's mass m and its directed distance from that point. And the mathematical formula for moment is equals to mass m times the distance d. The total moment m of a system of particles is the sum of the moments of all individual particles. The center of mass is the point on which a thin plate of any given shape balances. For two masses m1 and m2 located at x1 and x2, the center of mass x bar along the x-axis is equals to m1 times x1 plus m2 times x2 divided by m1 plus m2. This essentially means that the center of mass x bar is equals to the total moment m divided by the total mass. This is the same for a system of particles with masses of m1, m2 up to mn located at the coordinates of x1 and y1, x2, y2 up to xn, yn. So the center of mass for x bar is the total moment about the y-axis divided by the mass, while for y bar, it is the total moment about the x-axis divided by the mass. Here's an example. Given a system of three objects with the following properties. So the masses m1 is equal to 3 kg, m2 is 4, and m3 is 8. For the location, x1, y1 is equal to negative 1, 1. x2, y2 is 2, negative 1. x3, y3 is 3, 2. So firstly, we calculate the total mass of m by summing up all three masses, and we get 15 kilograms. Then we find the moment about y-axis, which is equals to m1x1 plus m2x2 plus m3x3, and we get 29. We also find the moment about the x-axis mx, which is m1y1 plus m2y2 plus m3y3, and it totals up to 50. Then we find x bar, which is the moment about y-axis my divided by the mass m, and we get 1.93. And we can also find the y bar by dividing moment about x-axis mx with the total mass m, and we get 1. So the center of mass x bar y bar is equals to 1.93, 1.